Okay, so hello everyone. So the topic that we're going to look at today is, on the MAC protocol. The protocol is called CSMA, CA, right? So what is CSMA? CSMA is Carrier Sense Multiple Access, right? And CA stands for Collision Avoidance. So this particular MAC protocol, where is it applied? It is basically applied in Wi-Fi. So the wireless stations, the wireless devices, goes on to implement this MAC protocol, uses this MAC protocol called CSMA CA. So this MAC protocol is applied in Wi-Fi, which is compliant to the IEEE 802.11 standard, which stands for the Wi-Fi, right? So the IEEE 802.11, standards basically gives the clear specifications of the bottom two layers, which is your physical layer and the MAC layer, data link layer, the MAC layer. So in the MAC layer, one of the protocols that's basically used by the wireless devices when they go on to use the shared frequency spectrum, the shared frequency channel, say in 2.4 gigahertz and all that, the CSMA CA protocol is widely adopted. So we will be looking at how CSMA CA works. First, we will try to understand that the previous protocol under random access category that we saw, which is CSMA CD, why is it applied only in wired, that is the bus topology by standard Ethernet station? And why can't it be applied on wireless, right? So that is the first thing that we will analyze. And then later we will look at, okay, why CD does not work and what is the solution of CA? What is the algorithm behind CSMA CA? But prior to that, let's quickly recap what does CSMA do. The CSMA stations are, basically the idea here is you listen in the channel, whether the channel is idle before you start talking. So if the medium is idle, you can transmit, right? So that's the idea behind this. So more technically, you go on to sense the energy level in the carrier frequency, right? And if the energy is not detected, which basically means that the channel is idle, you can contend for the medium, you can transmit. But here again, we understood that there is a vulnerable time where there could be a probability of collision, right? So what's the vulnerable time where you could have stations, frames getting collided is when a station detects the channel to be idle and starts transmitting. There could be a distant station who is still, thinks the channel to be idle because the signal is not propagated for him to detect the presence of energy. Prior to that, if he starts transmitting, having thought the channel is idle, right, the frames could collide. So there were different variants of CSMA, as you're all aware. One persistent stations which are following one persistent approach are P persistent or non-persistent. So the persistence idea here is if you sense the channel to be busy, you persistently keep checking till the channel becomes idle. And as soon as the channel becomes idle, if you transmit, certainly, then it's called one persistent. But if multiple stations are waiting to, capture, occupy and channel, then it could potentially lead to collisions. So that's where non-persistent came in, where you're not persistently checking the channel if the medium is busy. You randomly check at different times, and if the channel is idle, you transmit immediately. You could reduce the probability of collision, but that could lead to increased channel idle times. Channel has already become idle, but no one has occupied the channel. P persistent tried to actually take the pros of both of this, one persistent and non-persistent, where persistently you keep checking the channel till it becomes idle, and as soon as it becomes idle, you don't immediately transmit, but you transmit at the probability of P, right? You take a toss, and if it's heads, you transmit. Otherwise, you wait for a time slot. So the time slot duration is your vulnerable time, right? Which is your propagation delay. So after that time slot, if you detect the channel to be, busy, so the idea here is you take a toss. If you get heads, you transmit the slot. Otherwise, you wait for a time slot, and again you check the medium to be busy. Right, you'll have to persistently keep checking it. But if the medium is idle, so you transmit the probability of 1 minus P. So this is the idea behind P persistent, non-persistent, and one persistent. But despite that, the point here is there could be a probability of collision that can happen. So how are we going to handle collisions? That's where in wired, we are using the concept of collision detection. In wireless, we're going to use the concept of collision avoidance. So what does this CSMA CA, the collision avoidance, try to do? But let's now analyze how CSMA CD works. CD works basically when a station is transmitting a frame over the channel, it's not just going to transmit, but it is also going to simultaneously monitor the medium, right? So it's going to simultaneously keep receiving. If it receives its own signal, then the energy level is going to be the normal energy level, right? But then if another station also transmitted a frame and these frames are collided, what happens is that the energy basically, the collided signal adds up to the energy level. And so there's an abnormal energy that could be detected right over the channel by the transmitting stations. This is because a wired medium is a guided medium and there is not much signal that is getting lost in the transmission. So we could rather say that the received signal energy is almost quite same as the sent signal energy. The only factor that attenuates the strength of the signal is your distance, right? But there is not much other factors that could contribute to deterioration in your signal strength. So when two signals collide, then you could expect the energy level to double, right? And the transmitting station could detect this abnormal energy level and abort the transmission. And so it basically works in wired, and collision detection logic can work there. But in the case of wireless, the first problem that we have now is we are moving on to air as your medium, an unguided medium, and your signal that is getting transmitted, right, has to travel over your space, right? So when what happens is there's much of the signal energy that gets lost during transmission, right? So what happens is that the environmental factors also go on to basically affect the strength of the signal, which is not much of the case in your wired, scenarios. So having said, there are lots of problems in a wireless channel because wireless channel is a broadcast medium, right? And you're operating at a certain frequency range. Um, so what happens is if there is a collision happening by a distant station, you can't expect that double the energy to add up, right? Because the signal fading effect there's much of the signal which is there's already lost in transmission. And so an added up signal, could basically not make you effectively detect collision. And in wireless, it's like in half duplex. So simultaneously transmitting and listening on this same frequency is typically a challenge there. And so hence collision detection is not going to be effective in a wireless network scenarios, right? So having said, the algorithm that we're going to append to CSMA is basically going to be strategies of what we can do to avoid collisions. And that's where CA comes into place. The same logic of CSMA is there, which basically means you listen before you talk, right? And basically, you have the content to occupy the channel. So there are three strategies in place that are in the algorithm that tries to prevent avoid collisions, right? So the first strategy is called IFS. So what is IFS? IFS stands for interframe spacing, right? So this is the first strategy, which is again like similar to the persistence. So we will understand what is this IFS strategy to avoid collision. The second strategy is despite after IFS, that is you want to avoid collision by deferring the transmission, even if you find the channel to be idle. So that's the IFS period. After that, even after the channel is idle after IFS period, you have to content, right, by waiting for some slots, random number of slots. So that window during which you're going to wait, right, despite the channel being idle, is going to be different for different stations probably to avoid collisions, and that period is called the contention window. And obviously here in CSMA CA, we are incorporating the concept of positive acknowledgement, right? Which means that you want to know whether your transmission of your frame is successful or not. You are expecting an acknowledgement from the receiver, right? So this is the third strategy. But despite having all these strategies, there are still probability of collision that can happen. So we look at one scenario where there could be a collision probability that could happen, and how IEEE 802.11 standard handles such problems where despite the strategy collision could happen. And that problem is called as a hidden station problem. So later, as once we have completed our algorithm, we will look at this problem called hidden station problem. And what is the amendment made in CSMA CA in your IEEE 802.11 standard to handle this kind of hidden station problem where collision could happen? Okay, so let's get on to this. So if you look at this particular picture, I hope you can recall your persistent CSMA approach. So the first thing, this we are talking in terms of wireless devices MAC protocol, right? So wireless devices that are, say, contending in the 2.4 gigahertz, say, frequency band, right, on a particular channel. So basically has to sense the channel to see if the channel is idle or not. So the first thing that they try to do is, if the medium is channel is busy, they have to continuously keep sensing the medium, persistently keep checking the medium till it becomes idle. But as soon as the medium becomes idle, they're not going to transmit, unlike your one persistent station. But unlike a non-persistent, they're not going to do this approach. But like P persistent, they're going to wait for a period of time, which is called as the IFS period. Now let us bring in one logic here. So you all know that the vulnerable time in CSMA is your propagation delay, right? Your the max distance station, right? They think that the channel is idle and start transmitting, but the other distance station, to detect the presence of energy level, needs this propagation delay for the signal to propagate to detect that. But prior to that, if the station detects the channel to be idle, they start transmitting, right? So this, even after, if you find the medium to be busy, and once you find the idle, you wait for a period of time called IFS, right? So that if any distance station is already sensed the medium to be and started transmitting, after IFS, you check whether the medium is idle for you to see whether you can transmit. So that's the idea of bringing in IFS. So this is one main goal. You don't immediately transmit, but you wait for a period of interframe spacing. But this interframe spacing duration varies depending upon the priority of the frame. Varies depending on the priority of the frame. So what do you mean by priority of the frame? So, so let's classify this. Okay. So you have, say, normal data frames, which could be your email data or your file that you download that data, or it could be video frames or, audio frames, right? Or it could be some, so all these are conveying information. So you could either have your data frames or you could have your control frames. Control frames are like you're expecting an acknowledgement quickly, right? Or you've been looking at different protocols like ARP, right, and stuff like that. So there are handshake of some control signals, so control frames, which are you're expecting quickly, right? So these are something which you give more priority. Video frames you give more priority compared to email. So when you have different stations with different priority frames, right, the duration of the IFS waiting period could vary depending upon the priority of the frame. So a station which is having a higher priority frame could be given a shorter IFS period, which I call it as SIFS, shorter interframe spacing, compared to a station which is having a normal data frame, which we probably have a slightly larger interframe spacing, which is called as a distributed. D stands for distributed. These are all standard terminologies. Distributed interframe spacing, because all these are distributed stations. There's no control of any station. Any station can transmit at any time, any data, right? So having said, the duration of IFS could also vary, whether I need to wait shorter period till, if the medium is idle, or I have to wait for a longer period for the medium to be idle. So the priority station can capture the medium compared to a normal priority station. So that's the idea. But now the game is this: even after the IFS period, the medium is still idle. You can't immediately transmit, but you need to content in the contention window. So what do you mean by this contention window? So what you see here, the contention window is the time being divided into time slots, right? So let's get on further now. So prior to getting into the contention window, so IFS can also be used to define the priority of the station or the frame. Okay, so let's look at the contention window now. So the amount of time that you have is divided into time slots, right? So what is this time slots here? So even after the IFS period, if you find the medium to be idle, the station is actually going to choose a random number of slots as its wait time. Just like your BEB algorithm is your contention window, right? But then let me take you to the flow chart before getting onto this. Okay, so the number of slots in the window is going to change according to your binary exponential back-off strategy, right? So what we're going to do here, so let me show you the flow chart for much more clarity. So if you look at the flow chart here, you remember that K is the retry counter, right? So initially, for the first time when you're transmitting, you sense the medium to be busy, right? You persistently keep checking till the medium becomes idle. But as soon as the medium becomes idle, you're not going to transmit, but you're going to wait for the interframe spacing, which varies depending on the priority of the frame. But you're just trying to ensure that you have this vulnerable time cross to see if the channel is still idle after IFS time. So if the channel is not idle after the IFS time, you get into the persistent mode and keep sensing the medium till it becomes idle. But if the channel becomes idle after the IFS time, here is where you bring in your contention window logic. So the first time when when a k value is 0, right, your transmit is the first time, your random number that you're going to choose is either going to be from 0 to 2 power k minus 1, and k is basically 0. Your random number could be either waiting for one slot or transmitting immediately, right? So the idea here is, so depending on your R value, right, and the more retry that you're doing, your value of R could be in the range of your 0 to 2 power k minus 1. So you need to wait for R slots. But the interesting logic in this waiting time is that you're not just sensing your channel before your IFS and after your IFS, but during your contention window that we saw, right, in every slot, right, before and after every slot, you're going to sense the channel, right? So ideally, the concept here is you wait for R slots. That R could be 1 or 0 or any value of 2, 3, or 4 that comes in depending on your random number outcome. So you, even after the R slots, if the channel is idle, you start transmitting your frame. But the point here is this: different stations say has different R values, right? What could happen is potentially the other stations which are waiting because of larger R value, right, has to lose the chance, right? So having said, what are we going to do here is we are basically going to every station during the R slots, right? For every slot, after each slot, if it's going to check if the medium is idle. If it's idle, it is going to continue running its timer. But if it finds, say, after a few slots, right, it finds the channel to be busy, right? You know what is it going to do? It's basically going to pause the timer, right? Say, for example, R is 4 slots, right? After every slots, it's sensing the channel. But say after 2 slots, it finds the channel to be busy. So it pauses the timer, get into the persistent mode, right? And as soon as the channel becomes idle, it runs the timer and runs through the remaining slots, right? So which basically means that you halt and you start to continue when the medium becomes idle. So as soon as you're idle, if you wait for another remaining 2 slots and the medium is idle, you can capture the medium. So why are we doing this? We don't want the waiting stations, right, to hold long, and they have to be given the next chance if another station has grabbed the channel. So to ensure that the priority is given to that waiting stations, right, we this logic of halting the timer, pausing the timer, and continuing when it becomes idle can give more chance for that waiting station to occupy the channel next. So this is the idea that they try to bring in the contention window. The strategy here again is to avoid collision. At the same time, because of exponential backoff, the waiting station should be given the priority to transmit, right? So that is the concept that is brought here. So you send the data frame when the channel is idle and you wait for the acknowledgement. But if you're not getting an acknowledgement, if you're getting an acknowledgement, then the transmission is successful. But if you're not getting an acknowledgement, right, and the timer times out, you increment your value of k, and this time the back off goes like this, right? If its channel is busy, you get into persistent mode, wait for IFS, and then the contention window, the value of the R is now based on your k value. I hope you got the idea. So the strategies of IFS, the contention window, and the positive acknowledgement are incorporated here to try your best to avoid collisions in the wireless situations where collision detection is not possible. But despite all that, right, collision may occur and destroy the data. So one such scenario where the collision can occur despite all these three strategies is the concept of hidden station problem. So we'll analyze that shortly. But before that, I just want to sprinkle some key points on Wi-Fi, because we are all in two predominant technologies that's dominating our connection to internet. One is your Wi-Fi, another is your cellular technology. But Wi-Fi, as you know, is confined to a smaller space, right, within your home or within your university, right? So which is basically an extending and wired internet connection to wireless devices. Yes or no? So you have your router, wireless router. Till that it's wired, right? But then the stations which are within the access of that router or your access point gets your connections wirelessly to the internet. So that's the idea. So you want to extend a wired local area network, right, to wireless users using radio frequency predominantly. Now we've been using 2.4 gigahertz, 5 gigahertz, and all that. So there's been an evolution in that. Let me not get into much of this, but I just want you to talk from a perspective of the IEEE 802.11 standards, which is the project group which works on standardizing your Wi-Fi chipsets. We have gone through evolution in the generations from Wi-Fi 1 to Wi-Fi 6, Wi-Fi 7 now, right? So having said, the Wi-Fi stands for wireless fidelity, right? And it's a consortium, it's a Wi-Fi alliance, which basically certifies, the standards that comes in. So the physical and the data link layer specifications, if you look at the documents of your 802.11 standards, it would clearly give you what is all the algorithms that are used, the modulation schemes that are used in the MAC layer, what's the protocol that is used and all that. So this is the Wi-Fi chart where 1997, right, we started with the Wi-Fi 1. But then if you look at the 802.11 corresponding, this is for the layman to understand Wi-Fi 1, 2, 3, 4, 5, 6. Right, and all of you know that we are using now 802.11 AC, but we are moving towards 802.11 AX. So you see a lot of suffix symbols, which talks about every generation that has gone through every 5 years that we see a Wi-Fi generation, coming up. But obviously, the peak rate of the physical layer, the speed at which that we are able to achieve is so high throughput. So we are in a generation of very high throughput, right? From high throughput, very high throughput. We have not just operating in 2.4 gigahertz, we have gone to 5 gigahertz, and we're moving beyond 5 gigahertz, where we have lots of bandwidth and the schemes to transmit several spatial streams of data parallelly through multiple modulation schemes, that we are able to transmit more bits per second in per hertz. So that's called spectral efficiency, right? So that packing of so many bits transmitting per second has increased, and within the bandwidth that we have. So having said, this is basically the evolution that we have seen in the wireless standards. But one aspect is only we are focusing, which is on the MAC aspect, which is kind of a hard duplex channel that we have, where we can simultaneously transmit and receive on the same radio channel. So CA mechanism is something that is used, by the station. So let me not get into all these ideas. So having said, we said that collision detection might not work in the same frequency, where simultaneous monitoring not possible, and at the same time signal fading could prevent hearing collision by the distant station, right? So having said, despite this CSCA strategies that we have, there is a problem called hidden station problem. So what do you mean by a hidden station problem? So if you look at this particular picture, there are three wireless stations, right? BAC. And what you see here is this particular oval shape that you see is the communication range of B, or the transmission range of B. So B's radio range, right, is this much, that A falls within the radio range of B, right? But if you notice, this is the radio range of C, or the communication range of C. And A again falls in the communication range of not just B, but also in the communication range of C. What is interesting to note that C is not within the communication range of B. So whatever B talks, right, C will not be able to hear. That's the literal meaning of it, right? Similarly, whatever C talks, B will not be able to hear. So when B tries to sense the channel at that frequency, right, it thinks that the medium is idle, and it could probably start, say, talking to A. But C, when it sends the medium, it does not know that the channel is occupied because it's not able to hear it and it's not within the transmission range. So when B is talking to A and C senses the channel to be idle, and after IFS, it starts transmitting, right? What happens now is the sufferer is basically the receiver who's basically getting the frames from two different stations, right, which are hidden to each other. And so these frames gets collided at the receiver. At the receiver end, the receiver is only going to be affected, right? I might talk in the class and there could be other students also talking in the class. Who's going to be affected is potentially the receiver who's receiving the information is basically going to, be the sufferers. And hence, this hidden station problem where B and C are trying to talk to the same receiver, where B and C are hidden to each other, not within the range of each other, needs to be addressed. And that's where IEEE 802.11 in the CSMA CA algorithm tries to, bring in one more strategy in order to see whether is there any hidden station there. They should be prevented. Either B should talk or C should talk, not both, during that same contention window, right? So having said, the strategy that we're going to discuss now is to address hidden station problem. So this is again another scenario where station B and C are hidden to each other. There could be some obstruction also could actually, basically block the radio coverage. That could also make it hidden rather than the range problem. These kind of obstructions can also make the stations hidden to each other. But despite that, the problem is these are trying to talk to the same receiver. Right, this could be your Wi-Fi, your router, and there are two stations which are distant apart, right? So the having such scenario, let's look at what is the strategies in place. So now CSMA CA algorithm brings in two control frames that are going to be exchanged by the stations that are going to communicate. Right, these control frames are not going to carry data, but they're going to carry an information. Hey, I want to talk to you. Can I talk to you? Right? So that kind of an exchange is going to happen before you start transmitting your data frames. So what are those two control frames called? The first control frame is called as RTS, right? RTS stands for request to send frame. RTS stands for request to send frame. So who is going to send the request to send? The sending station, the transmitting station, the B who wants to talk to A will first send a request to A. Can I talk to you? Right? I'm going to talk to you. Say I'm going to take your talk. I'm going to take your lecture for the next one slot. Now for the next 50 minutes. Are you ready to receive? Right? So that is what the first thing that is being sent, and you expect from the receiver a clear signal. Yes, sir, you could go ahead and you could talk for the next 50 minutes. That frame is called CTS frame. CTS stands for clear to send. Right? So this clear to send is going to be sent by the receiver. And the interesting aspect now is, since it's a wireless medium, right, and all the stations, so if you look at B and C, right, that is there, though they are hidden to each other, A is a common receiver and A's range, right, both B and C falls under. So when A tries to communicate, telling a clear to send signal, since it's a broadcast medium, though it has been addressed to B, the stations which are within the range of A, right, can also hear that signal. And so if they understand that, hey, come on, these guys are going to talk, sir is going to talk for the next 50 minutes, and A says, okay, right, I'm able to hear, and I got that to know that, then they will not talk during when B is talking. So that is the intention that they try to bring in. So let's understand this more technically now. So I want you to understand that the source says B, the destination says A, and these stations are hidden to B. Say that is your C or D or whatever it is. So first thing that we try to do here is, this is a very short frame, control frame, which is called RTS, request to send. So what is this RTS frame going to contain? It's going to contain the source MAC address, right? It's going to contain the receiver MAC address, right? And it's also going to contain one more field, which is called how long I'm going to transmit, the duration of how long I'm going to occupy the channel. So this is going to be there in the RTS. And when this RTS frame is received by the destination, right, by A, and A is now saying, okay, sir, you can talk for the next whatever is the duration. And he tries to address it back to the source. But the interesting aspect is, since it's wireless, the CTS signal propagates in all directions. Though CTS is addressed to from A to B, and it copies this duration of how long he's going to stay to talk to him, say for 50 minutes, right? He goes on to copy that value in the CTS frame field and sends it. So not just this station, okay, gets a clear signal that he could go ahead to talk, but all the other stations understand that, hey, come on here, B is going to talk to A, right, for 50 minutes. So I should all not talk for this duration. And so what they basically do is, all these hidden station, according to the standard, it is called as NAV. NAV stands for Network Allocation Vector. Network allocation vector. So network allocation vector is the time of period, right, of how long. So I copy this duration of transmission, right? So how long I should keep my transceiver shut off, which basically means I should not sense the medium or transmit during this period. After this timer only, right, after this network allocation vector expires, then only I can go on to content for the channel. So they all set their timers depending on the duration of the transmission. And so during that time, when these hidden stations are shut, the source can send its data frame. So data frames generally are longer. And so for every data frame, you have to content like this, right? So the destination, if it got the data, it's going to send an acknowledgement, and this acknowledgement is going to also be received. So this, why it's showing propagating in all directions, is because it's a broadcast medium, right? So everyone will receive, but this acknowledgement is addressed to be, right? So once this NAV expires, then only the other stations can actually content. So any station which has to content for the medium, right, despite following your CSMA, CA, IFS contention window strategies. But the point here is, before sending your data frame, he has to send RTS, get a CTS, and then send your data and wait for the acknowledgement. And here I was talking about the interframe spacing, if you remember, that varies depending on the priority of the frame. So if you look at the CTS frame has more priority, and the acknowledgement frame has more priority compared to your normal data frames or RTS frames. And hence the waiting time of RT, sending an RTS frame is a slightly larger. It's called the DIFS period, compared to sending a CTS frame by station A or acknowledgement by station. They only wait for a very shorter interframe spacing if the channel is idle, right? And they try to send this. Even for the data, it's DIFS period. So I hope you're able to understand this handshakes that happens. Two handshakes, RTS, right? Wait for a CTS. But if you're not getting a CTS after you send an RTS, now that is an interesting point. So even though there are multiple stations that are waiting to send, they all try to send, say, RTS during the same time. What happens? The RTS from the other station also comes in. RTS can collide, but the data has not got corrupted, right? You're sending a request and request got damaged, right? You're not getting a CTS. Then what happens? Again, there should be a timer, right? So you again retry, like your back off, sending a request again after some random amount of time. So this way, you could prevent the data getting collided, right, by the hidden stations who are trying to transmit, and they basically have their hidden stations set their timers so that they could prevent collisions by hidden stations, right? So that's the appending that has been done with CSMA CA. So I hope you understand the idea of bringing in request to send, clear to send, and finally the hidden station setting up a timer depending on the duration of the transmission called NAV, and they can only go on to sense the channel after the NAV period and transmit their data waiting, right? So collision can also happen. The backup strategy basically helps to pull that. Thank you, guys. Thank you for the patience. So we will continue the rest the next class. Thanks.